circular motion, what does it take? It's a privilege, not a right. A lot of things have to go correctly before you manage to do it. The requirement is you need a certain amount of force toward the center. We call this the centripetal force, so when you hear centripetal, think required. The amount of force you'll need depends on the mass, the speed, and the radius of the circle you want to make. And the force has to be toward the center. You've got to hug it, but hug it not too tight. This must be provided by one or more actual forces, some real-world forces, things like normal force, friction, gravity, tension, things like that. And if the actual amount of force isn't enough, if the actual does not meet the requirements, well, you haven't hugged it tight enough, you'll fly away, fly out of the circle that you're trying to make. If you hug it too tightly, the actual force to the center is bigger than the requirement. You'll hug it so tight you squeeze and strangle the circle, it'll collapse inward. This is the just right, okay? When the actual amount of forces are providing just the correct amount of force based on what you've calculated is required, and then you get to go in a circle. And so what I want to do from here is go back to the example that I sketched out last time. I'm not going to do this as a formal example with numbers. I'll do another one after this one. Here I just want to kind of sketch out and talk through what happens. Okay? So what I have is a person who is swinging a bucket in a vertical circle here on Earth like this. So let's take a look at the physics. First things first, I should mention that the speed at the top, I guess I'll call this 0.1, may not be the same as the speed through the bottom. So I should probably call the top 0.1 and the bottom 0.2. Now that's just something that you have to accept for the moment, that it speeds up as it goes downward. Hopefully that's not unsurprising, because things tend to go faster when they fall because of gravity, and gravity is actually the thing that's responsible for that speed up. We'll learn something later called the energy method, where it turns out to be very easy to compute how much it speeds up. But for right now, let me just refer to those two speeds as different speeds. Okay? Now what we did do last time, and I'll recap here, was we cataloged the forces that act on the bucket at the top and the bottom of the swing. So what we have is that tension always pulls, so it's always should point away from the bucket, and so the tension pulls downward here and upward here. So it's always away, always pulls, never pushes. And gravity always pulls downward no matter what, so gravity pulls into the circle at the top but out of the circle at the bottom. Oh, and I forgot to label here, I should probably label these tensions in general may not be equal, so this is T at the top, this is T at the bottom, T1 and T2. And so I'm not going to do this as a formal example, I'm just going to kind of write down the force equation at the top and at the bottom and look at them and make sure we understand it. I guess let's start at the top, which I've labeled 0.1. Now, just like with any other force problems, if you start to have a bunch of multiple forces going around, you might consider setting an axis, right? What are you calling positive? So what I would like to do, if this doesn't bother anybody too much, since both of these forces are acting downward, I want to set downward to be positive, so then I can say they're both positive instead of having them annoyingly both be negative. Not that there's anything wrong with that, but is that okay if I set the plus direction to be like that? Okay. So we know this is going in a circle, so we put on the left-hand side the actual forces that act. There are two. There is the tension, and there's the force of gravity. Once again, we can see the utility of not having G have a negative inside it, because we don't always want it in there. G is not negative. Okay? So those are the actual forces. And we need those two to form a team to get me the right amount of force. And of course, the force toward the center is this. So on the right-hand side, I'll put what is the requirement. So I'll put mv1 squared over r, and to make sure it's toward the center, I want to put a plus there. Okay? So I have two forces toward the center, which I'll call plus, which give me the requirement that you have to meet toward the center, which is plus. Okay? So be aware that sometimes making sure this force is toward the center may require some kind of signage. Okay? Towards the center may be reinforced by a plus or minus, just like any other quantity. When you want to make sure it points the right way along an axis, you put the right sign in front of it. So, that's the equation in general. And what I want to do now is take a look at some scenarios. So some scenarios, first of all, the weight is the weight, right? So let's say the weight, let's say for example it's 10 newtons, okay? Now, let's say you're going super fast. You're going super fast and you need 50 newtons toward the center to hold this turn, right? So you're going fast enough that you need 50 newtons to hold the turn. Well, gravity's inward, that'll help, but it's only 10 newtons. So how much does the tension have to do? 40. So these guys form a team. Gravity always kicks in 10, and the tension has to make up the rest. All right? So you can see that you need a force toward the center, and here you have not one but two forces which are doing that. If you swing a bucket in a circle fast enough, you'll feel a strain in your arm even at the top, okay? Because your arm needs to pull down too. Gravity can't do it alone, you have to pull down too. It's going so fast that it will go in a straight line unless you hold the turn by 50 newtons, and 50 newtons, if gravity doesn't cover it all, you got to exert the rest. Now, let's slow down. Let's say we only have, you only need 15 newtons toward the center. You're going slower, and when you go slower, you don't need as much force to hold the turn. Now, gravity kicks in 10, right? How much does the tension need to put in? 5. They form a team, and now gravity's putting in the majority. Well, gravity just puts in a fixed amount, right? It's like if you have a friend where you go out to a restaurant and they always put down $20 for the bill, no matter what. Okay? You probably don't want to go to expensive restaurants with that friend, okay? Where if the bill is 50 bucks, they kick in 10 bucks and you have to put in 40. If you go to a cheap restaurant, they always put in 10 bucks. You actually get to pay less if you go to somewhere where the total bill is less, right? Okay, so think of gravity as always putting in a fixed amount, and the tension needs to make up for that. Does that make sense? In fact, let's slow down even more. Let's slow down so that you only need 10 newtons toward the center. Well, gravity's 10 newtons. What does the tension need to be? 0. If you go into a restaurant, the entire bill is 10 bucks, your friend always puts in 10 bucks, you eat for free, right? Have you ever tried this? Slow it down, slow it down, slow it down, and then it seems to go up through the top by itself. You don't need to exert any tension. Gravity is providing the centripetal force all by itself. Why doesn't the water fall out of the bucket? Well, gravity at that moment is not making the bucket, the water fall inward, it's making it fall continuing on the circle instead of going straight. That's the role that gravity is playing at that moment. Gravity is serving to, instead of letting the bucket go straight out, it's serving to pull it down into the circle. So what we find is that it is possible at the top for the tension to actually turn off. The two, generally speaking, will both contribute to the centripetal force, but if gravity has it covered, then the tension doesn't need to do anything. Now, by the way, what happens if I slow down even more? Maybe I need 9 newtons towards the center. Can I make that happen? There's no way, because gravity puts in 10. So even if the tension turns off, you can't turn off gravity. So now you failed. Going too slow. What happens when the actual amount of force pulling toward the center is bigger than what you need? Like this. You collapse inward. So, we don't have that. We don't want that, right? Going in a circle is a privilege, not a right, and we have failed in satisfying the equation for it now. So if we back it up, this here, this line, is kind of the end of the road. We basically figured out when you go to V min, the tension goes to 0. Which is to say that you're going so slow that the force of gravity can provide the centripetal by itself. It doesn't need any help. So that's often how we find these extreme cases, is by thinking about what forces are involved, and one of the forces can potentially go to 0 because the other one's got the whole thing covered now. If you go faster, tension is going to not need to start putting in some, but at the slowest speed, gravity's got it covered. Are there any questions on that before I move on to the point 2? Okay. So here you see that these two form a team. The tension is possible to be bigger or equal or maybe smaller. It depends really on what total requirement are you trying to meet. So the tension always makes up for what the gravity doesn't provide. Okay? Let's do point 2. Point 2, we have forces going upward and going downward. So one of those forces is going to have to be negative. I guess, just for the sake of argument, I'll set this way to be plus. So the bottom, I put my actual forces on the left. I put my requirement on the right. So now I'm going to have tension acting toward the center, gravity acting away. And which way do we want which way is the force required to be? Positive, toward the center, right? Yeah, question, yeah.
In the same problem, you can set the direction, the positive direction twice?
Yes, essentially, because we're just kind of writing down two things that don't have really anything to do with each other, right? So if we want to, we just have to be really careful when if we were to try to combine them, but we're not, right? We're just looking at two different locations independently and asking what are the conditions that allow it to stay in circular motion at that moment. Let's suppose, for instance, that we compute, based on our speed, that you need, I don't know, 70 newtons to hold the turn. Okay? You need 70 newtons toward the center. And let's suppose gravity is 10 newtons still, but it's 10 newtons the wrong way. We need 70 newtons inward. I guess I should label that as plus, and we have 10 newtons outward. We've got problems, right? How many newtons do we need the tension to be? 80. We need the tension to be 80 so that when gravity actually takes 10 of those away, we're still at the required 70 toward the middle. The tension has to work that much harder because one of the forces, now the force of gravity, is pulling outward and we need the force to be inward. So in this case, the tension will always exceed gravity. You have an inward force and an outward force. And the only way you're going to meet your inward requirement is if the inward force always wins. Note, by the way, that the tension can be substantially larger than the gravity force. Now, if you want to see some people who don't understand physics, you need to go no further than YouTube and watch people failing on a rope swing in a spectacular manner, okay? Now, if you were just hanging at rest on a rope swing, you just need to support your own weight, right? Because you're at rest. You're not accelerating, the net force is 0, which means that the tension needs to cancel the weight. But just trying to hang on a rope swing at rest, people think, oh, I can hold this, and then they climb up into some big tree, right? And they try to swing down like that, and you'll see plenty of people when they get to the bottom tearing off the rope and just going flying away. They can't hold their grip. Anyone has ever seen this in person or possibly? Right? You hope it's over water, because if they lose their grip, they're going whoosh out in a straight line, right? So they go like that. That's because the tension that you need to maintain at the bottom of the swing is far larger than your own weight. And if you're not strong enough, you're not going to make it happen. Okay? When you're going through the bottom of the circle, these two don't cancel. If they cancel, you'd go in a straight line. But you don't. You curve up. So the upward force is going to have to win against the downward force. The tension is far bigger than the weight. Does that make sense? So again, remember, when you go in a circle, you need a force toward the center. And if you have forces acting the wrong way, outward, then the forces that act inward are going to have to be that much bigger to make it happen. So here the tension needs to be 80 newtons, so you get 70 newtons toward the center and maintain this particular circle. Okay? Are there any questions on this example before I do another one numerically? Okay, let's do another one. This time, instead of just kind of talking through the various cases, I want to actually do it numerically. I have a car. The car is on cruise control, which means that it maintains a constant speed no matter what. And let me say that that speed is 10 meters per second. That's not very fast. Just rule of thumb, multiply by 2 rule, it's about 20 miles an hour-ish. Fairly modest. Okay? Let me say the mass of the car is 100 kilograms. That's a tiny car. It's like a go-kart or something. Anyways, I didn't want the number to be too big because it'd be kind of annoying to work with. And then this bump that it's going to go over, let me say that I can approximate it as a circle of radius 20 meters. And here's going to be my question. What is the normal, I guess I forgot the label here. I'm going to ask about the car at the top of the bump too. And the flat road, I'll label point A. The crest of the hill, I'll label point B. I want to know the normal force provided by the road in both cases. All right? So let's start with the baseline, the flat road, right? So the force of gravity acts here, as does the normal force. How do those relate to each other?
Same size, different direction.
Same size, different direction. So I can calculate the amount of force that is exerted up by the ground at that location to make sure the car doesn't go into it is 980 newtons, if I multiply mg correctly, which I have, yes, okay? So what happens? Well, these two cancel, and of course there is no vertical acceleration of any kind. This thing just continues to go in a straight line, right? Well, moving on to point B, that's not going to happen because if these, not to jump the gun, how many forces act on the car vertically at point B? How many people say 0? 1? 2? 3? Good. 2. Same 2. Force of gravity. And normal force. Centripetal force is not a third force. It's a requirement that these two actual forces have to meet. But now they don't cancel. How do I know that? Because if they cancel, you would go like this. And you, of course, do not start levitating above the road. You're not going to go in a straight line anymore. You have to curve down because you want to maintain your circle. So if you want to curve down, then which force is bigger, the down force or the up force? Down. So we're predicting that now the normal force has to lose and gravity actually has to win. Now, of course, it's not that gravity gets stronger, it's that the force from the road has been diminished. So let's write down the equation for this. Let's give the other direction a chance. We typically would set positive like this. And in this case, toward the center will be in the negative direction, right? Downwards is toward the center. So at point B, the actual forces we have an upward force, we have a downward force, and then the requirement, what do I put over there? How much force is required to hold a circle? mv squared over r, and then should I put it plus or minus? Minus, right? Because now toward the center is minus. That's towards the center. So in summary, what am I writing down? I'm saying I have one force that's away from the center. I have another force that's toward the center. I need my overall force to be toward the center. Toward the center, I've just notated as negative because why not? We should be able to do it either way. So this positive force is away from the center. This negative force is toward the center. We need the overall force to be toward the center. Now you can work out, you can solve for n right away, but let's again look with the numbers. If you plugged in this mass, this speed, and this radius, you will find that this should come out to be 500 newtons in the negative direction. I need 500 newtons toward the center. Okay? If I want to take this mass with this speed and this radius of circle, I need 500 newtons to hold that turn. If I provide not enough, it'll fly away. If I provide too much, it'll fall inward. 500 newtons is just right. So let's go and see how the real world allows that to happen. Well, the force of gravity is actually 980. It's too much. Okay? What normally happens if you pull too hard into the circle, more than you need? Pull it inward, right? I erased it, but I had that right. If the actual force toward the center is more than you need, you collapse it inward. Except here, the ground says, whoa, 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 whoa. You can't collapse this circle. I'm the ground. I'm right here. You can't come in here. So, of course, the normal force says you can't actually come in here, and it balances out. But notice it doesn't have to cancel off the 980 in its entirety. It just has to cancel off however much of this is the too much. Okay? This will need to exert 480 the other way. if it exerts 480 the other way, then the 480 minus 980 gives you 500 newtons toward the center, negative 500. Now, is that in danger of smushing the surface? No, it's not. In fact, that 500 newtons toward the center just keeps you going along the road instead of flying away. So this just needs to cancel, as I'll put it, as cancels the overage of mg. So however much is too much. And so you notice that the normal force here is not nearly as much, just like we predicted, right? The normal force is normal force is less than the force of gravity because it doesn't want to cancel all of it to protect the structural integrity of the surface. It just needs to cancel off whatever of gravity is too much. The first 500 newtons of gravity is just fine. It provides you this. It's the extra 480 that's too much. Okay? So we find that the ground does not exert as large of a force now. Okay? We solve here, ND would be 480. So this is where I can point back to something we learned on homework number 4. The elevator problem where we learned about apparent weight. So we learned that both the scale reading and your apparent weight go with your normal force. So how do you feel when you go over this bump? Do you feel lighter or heavier than usual compared to this? You feel lighter, right? So you're going to feel lighter. Has anyone ever experienced this going over a bump? You feel lighter? You might even achieve an apparent weight of 0 if you hit a bump hard enough, right? And the reason why is that the ground is just not pushing up on you as hard as it usually does. Normally the ground needs to cancel off your force of gravity in its entirety. But if you're trying to make a circle that the center of it is below you, the force of gravity is actually providing the centripetal force, and the normal force may be much smaller or even 0. Okay? Now, I might point out, I can sketch out the elevator example, how we did before. We, of course, if we're in an elevator that's accelerating downward, then the net force is downward. And so what we concluded is that the downward force, force of gravity, has to be bigger than the upward force, normal force. It's the exact same thing. You feel lighter in an elevator, you feel lighter going over a bump. In both cases, it's because the force is downward, the net force is downward, which means that the normal force is smaller than the gravitational force. Now you might argue, these seem different somehow. Well, it's certainly true that if you're in an elevator, if that's the bottom of the elevator shaft, you're certainly changing your distance from it, right? You're going to either get closer or further from it. That's because you're just moving along a line. Well, remember, and in a circle, you do also have a net force and acceleration toward the middle. The only thing that's kind of weird about a circle is the fact that you're accelerating towards a point that you never get any close to. Now, if there weren't force that way, you'd fly away. But in this case, what happens in a circle is you happen to have sideways motion. So you happen to have sideways motion, so that means that as you quote-unquote accelerate toward the center, you don't actually ever get any closer. You could do the same thing over here. If you had an elevator that you had moving extremely fast, then you could actually not change your distance from the from the bottom of the elevator shaft. By the way, at this point, the elevator would be in orbit, okay? Because it'd be going around the entire Earth. In fact, that's the next order of business. We're going to talk about orbits. Orbits are simply where you're free falling. The force of gravity is providing the centripetal force. You just happen to be going so fast that as you fall toward the Earth, you never get any closer to it. Are there any questions on this example before I do some orbits? All right, let's knock out some orbits. This is a synthesis of the two topics we've just done. Universal gravitation, we know we can find the gravitational force anywhere we want, and orbits, the force of gravity provides a centripetal. Let's do it. I'm going to take the Earth, and I'm going to take our oldest satellite, the Moon, and there it is moving up there in the sky. Now, if it didn't have a net force on it, it would fly away, but we know it doesn't do that. What keeps it around? It's its gravitational attraction to the Earth. That's what holds the turn. The Moon is a state of perpetually falling toward the Earth. It just happens to be moving fast enough to the side that it never falls. Oh, and let me label, I should put in here more proper labels. Mass of the Earth, I'll call capital M sub E, and the mass of the Moon I'll call lowercase m. I guess let's call it uppercase M sub m, mass of the Moon. So the force of gravity acting on the Moon is just right. Provides exactly the amount of centripetal force. Now you might wonder, how did that kind of state become to be? How does the gravity happen to be exactly the right amount? Well, we used to have lots of other stuff where it wasn't the right amount, right? There used to be other debris where the amount of force that gravity exerted on it was too much. Those got pulled down to Earth. Others, it wasn't enough, so it flew away. But there's bound by chance to be some stuff that ends up being just right. Okay? You might argue that there's also a mutual force pulling back on the Earth, which there is. Newton's third law. The only reason why the Moon orbits around the Earth, not vice versa, is because they're relative masses. Okay, so that force is not as big of a deal to the Earth because it's more massive. So let's work out the details. Let's find out what's going on. We put in our universal gravitational law. That's what's providing the attractive force. And then, of course, our requirement on the other side is mv squared over r. Now, which mass should we use for that? What's actually being taken in the circle? The Moon. So we put the Moon's mass times its speed over r. This is going to allow us to solve for the orbital speed of the Moon. If we know how far away it is, we can find out how fast it's going. First of all, I should double check if that's the same r. It is. So the universal gravitational law, it's the center-to-center distance. And this is the circle radius. So that's the same r. I can do some cancellation there. One of those r's goes away. And the mass of the Moon cancels, because it appears on both sides. So it might seem counterintuitive, but the speed of the Moon doesn't depend on the Moon itself. In fact, if we solve here, we get this equation. This is not intended to be a derivation. You should be able to get this yourself. Question?
Is it true for any other planet as well?
Well, it doesn't depend on the Moon's mass, but it does depend on the distance, right? It's the distance away you are from the Earth. So the Moon's mass doesn't matter, but it does change with radius. So if you wanted to put, some friend you didn't like very much up in orbit at the same distance, you could give them the same speed, and they would orbit. But it does depend on how far you are away, right? You can see from this equation that if you go further away, then you can orbit slower. It may be surprising that the moon's mass doesn't matter, but remember that even though you need a lot more centripetal force to hold a large mass in orbit, gravity is always nice to step up and exert a larger force on a larger mass, right? That's why we found out that the gravitational acceleration was independent for all objects. So, if the moon has more mass, does it need more force to hold in a turn? Yes, and gravity automatically exerts more force too. So, let's find out the orbital speed of the moon. Now, I've given you in past lectures the universal gravitational constant. I've given you the mass of the Earth. They're also available on the formula page. The radius, that is the center-to-center distance between the moon and the Earth, is 3.84 times 10 to the 8th meters. Although, whether that's center to center or not is actually largely irrelevant, because that's already 100 times larger than the radius of the Earth itself, so it starts to not really matter. That's like if I had held a grain of sand in this hand and a grain of sand in the other hand and told you the distance between them, you worrying about if it's center to center or not. Doesn't matter. The distance between them is much greater than their size itself. So all I need to do is plug that in here. It tells me how fast the moon is going. And the moon is going around us at 1,018 meters per second, which is about 2,300 miles per hour. The moon is zooming up there very fast. Okay? So why don't we see the moon go zoom across the sky? If it's moving that fast, it's also very far away, right? If a car came by right under your nose at 80 miles an hour, zoom, looks a lot different than if it's going 80 miles an hour in the distance, right? You may notice that the moon rises and sets every night, just like the sun. That again has nothing to do with this. It has to, you guys know why the sun rises and sets, right? The Earth just turns into it and away from it. Same reason the moon does. In fact, you would have to very carefully check the moon against the background stars to be able to even tell that it is progressing. So you'd have to take out that rising and setting of the moon that's due to the rotation of the Earth. You could carefully check it across the background stars and see that it is progressing. It does make a circle. Let's figure out what that circle is like. We can take the speed as distance over time. If it's moving at a constant speed, we don't need any fancy constant acceleration equations. We just use basically distance equals rate times time. Can anyone tell me what's the distance around a circle? 2 pi r. We call it the circumference sometimes, just to be fancy, right? And for the time, I'm going to give a special letter, capital T, which is called the period. The period is the time it takes to do something that happens over and over again. It's the time for it to do it once. So I could solve for the period. I'll invert this equation. It'll be 2 pi r over v. And I can find how long does it take for the moon to make one journey. How much time does it take for the moon to make one trip around the Earth? And if you put in everything in SI units, you'll get 2.37 times 10 to the 6th seconds, which may not look like much until you convert it out. It's about 27.4 days, which sort of rings a bell. That's about what amount of time? A month. Well, this is the original basis of a month. Of course, when our ancestors were coming up in the world, right, they needed to tell something more about time besides just day and night. The day I'll go hunting, and the night I'll come back in because I might get, eaten, okay? But then, you're inviting your caveman friends over. Hey, why don't you come over for dinner on the next full moon, right? So it's a convenient way to tell time. Now, they of course didn't do these calculations as cavemen. How do you know that the moon has gone through one complete cycle? Phases of the moon? Yes. So, if you look at the sun is over here, put the comic sunglasses on the sun here, okay? Well, the moon, whichever side is facing toward the sun is lit up. I guess I should back up. You guys know that the sun the moon is not the source of its own light, correct? Okay, I had to clarify that once. So, the moon does not glow on its own. How would it know to glow glow, right? Anyway, it's reflected sunlight. So the side that's away from the sun is in shadow. I can draw it here on its trip around its orbit. So the side that is pointed toward the sun is lit up. What do we see from Earth here? Half moon, right? What about over here? Full moon. We see the lit up side in its entirety. How about here? Half moon-ish. And then here we see new moon, right? We see the shadow part. Okay. Now the cycles of the moon, in full disclosure, don't go as 27.4 days. They go as 29.5 days. It's not that the calculation is wrong. Here's the thing. This takes long enough that the Earth itself has completed part of its orbit. So if you start here with a full moon and you go around, right, you notice with the full moon, the moon, Earth, and sun have to be lined up. By the time you've gotten back around here, the Earth itself has moved a little bit, so you have to go a little extra to get them to all line up again. So the phases of the moon actually go a little bit longer. They go as 29.5 days. So the phases of the moon is close, but just a smidge longer, about 29.5 days, just because it's actually a little bit more than one period. It has to go around once plus a little extra because the Earth moves from the middle of the circle too, as it goes around the sun. So if that isn't close to a month, convince you that that's the basis of a month, I don't know what to tell you. In fact, the Chinese calendar still does use the lunar calendar, right? Okay. Now in the Western calendar, right, January through December, we have moved to a solar calendar, right? One where we do the Earth around the sun, right? We do that instead? Yes? Okay. Now why do we do that? Well, the reason, of course, is that if you're going to stop being a hunter-gatherer and you're going to settle down and have an agricultural lifestyle, you need to plan your growing season, stuff like that, around the weather, right? So that's why we moved in the Western calendar to a solar calendar. And since, of course, they're independent rotations, the moon around the Earth and the Earth around the sun, that number doesn't fit evenly into a year. So we kind of have a vestigial idea of months, even though the months are now 30 and 31 days and sometimes 28, right? So we still have the general idea of the month in a solar calendar, even though this was its original source. Let's do that one. Here's the sun, here's the Earth. By the way, I should check. I should mention, again, this is common misconceptions. The orbit is nearly circular. The fact that we have seasons is not due to the proximity to the sun. Okay? In fact, we're close up in this hemisphere. We're closer to the sun in the wintertime. Okay? What is it that causes seasons? Can anyone tell me? Yeah.
Axial flare, like
That's the tilt. That's exactly the tilt of the Earth, right? That's why they have summertime in Australia when we have wintertime here, right? It's about who's tilted away versus toward the Earth, right? If our planet didn't happen to have a slight tilt, we wouldn't even give a crap about the trip around the sun. We'd probably definitely be on a lunar calendar because then they would have no bearing. The weather would be the same all the time, okay? So let's just switch out. We basically already did this problem. Now the mass in the center, it used to be the Earth. We should switch it out for the sun. And then the mass going around, which, by the way, as you remember, actually cancels out. That used to be the moon. Now it's the Earth itself. So let's write it down. So I'm going to tell you the answers, plugging into the same equations, just plugging in the right things. I guess I should tell you the mass of the sun, which that's not in your notes. So here it is in your notes. And it is on the equation sheet as well if you ever need it. How fast are we going around the sun? 3 times 10 to the 4th meters per second, or 67,500 miles per hour. That is how fast you are currently traveling around the sun. Okay? Now, before you wonder how we are we not holding on for dear life, zooming through the cosmos, we don't feel velocity, right? We don't feel any different if we're moving fast versus slow versus at rest. Newton's first law tells us that they're equivalent. What you notice is acceleration, right? Think about it in an airplane, right? You don't notice you're going 300 miles per hour. You notice when there's turbulence, right? You notice when you have turbulence. In this case, you might question, if we're going that fast, it seems like our centripetal acceleration will be vast until you remember that we're doing an extremely gradual circle. The centripetal acceleration we have around the sun is minimal. You don't get nauseous riding the Earth, okay? So you notice acceleration, and the circle is so large, it, for all intents and purposes, is barely different than a straight line, right? Let me tell you a little bit about the period. If you work out the period by this equation, it's 3.16 times 10 to the 7 seconds, which is about 365.77 days. It's not bad for our calculation, considering we use round-off numbers. What is the exact number? 365 and... a quarter? What's the quarter days? Leap year, right? Why is it such an ugly number? To which I will say, why shouldn't it be? Completely independent things. Rotation of the Earth around its own axis, trip around the sun. It's not a nice number. We're lucky that it's about a quarter. Therefore, we can have something called a leap year, right? Now, if you're wondering if that's coincidence, that's a quarter. It's not a quarter. The real length of a year that's the real length. We round up. It's actually 11 minutes short of a full quarter. So you might say, who cares? It's 11 minutes in a whole year. Well, here's why you care. If you are 11 minutes off in the same direction every year, if you use that calendar long enough, you got severe problems. And that's exactly what happened in the year 1582. People were starting to wonder, why is Christmas starting to be in the spring? Why is Easter starting to be in the summertime? Because at that point, that 11 minutes difference had accumulated into 10 days. So, problem. So the astronomers told the Pope, and the Pope told everybody, hey, you're going to wake up, you're going to go to sleep on September 5th, you're going to wake up on September 15th. Okay? So people were very confused by this, and also all the Protestants weren't going to do what the Pope said simply because he was the Pope. So there's a problem. Well, we don't use a 365.25-day calendar. This strict calendar, which is called the Julian calendar, has been replaced by a calendar which tries to account for this extra 11 minutes. We don't have leap year every 4 years. I don't know if you didn't know that. It's understandable because it will never happen in your entire lifetime. The last time we skipped a leap year that was scheduled was the year 1900, and the next time we'll skip another one when it's scheduled is 2100. Your entire lifetime will not span one of these years, but we do not have leap year every 4 years. We use a modified calendar that accounts for the fact that this 11-minute discrepancy exists. There's a lot of crazy history that I unfortunately ran out of time today, but I'll start a new topic next time.